Today's lesson will focus on the titration curves that get set up between an acid and a base neutralization. We are already aware of titrations as a really precise technique of determining concentrations of solutions. Oftentimes they are used in neutralization reactions, but not always. We can use a titration in just a displacement reaction, some other kind of reaction to determine the concentration of any kind of solution. However, in an acid-base neutralization, titration is the best way of determining the exact moment when an acid and a base are completely neutralized. When this happens, this is called the equivalence point. And the equivalence point will occur at a variety of pH values depending on what type of acid and base you are reacting. If it is a strong acid, strong base, a weak acid, or a weak base combination, the equivalence point will happen at a variety of pH levels. Titrations allow us to set up curves or graphs that enable us to graphically analyze this equivalence point. So in general, titrations have involved either the addition of a strong acid or a strong base, or both, in order to complete a neutralization reaction. And we now know that these titrations will not always yield an equivalence point of a pH of 7. And this is where we are now aware, depending on the type of acid and base that you use, the salt that gets created may actually have ions, conjugate acids, conjugate bases, that will hydrolyze in water and influence the pH of the solution. So to summarize some terms that were learned back in grade 11, the term neutral point, which we often would use when we say that we're neutralizing an acid and a base, and this applies or implies a pH of 7, this is best avoided, this term, because again, we don't always have a pH of 7 in a neutralization reaction. The term equivalence point means that the reactant solutions have been mixed in a perfect proportion so that none of them are remaining, only products are remaining. And then the term endpoint, which you might recall from last year, is the point where if we've added an acid-base indicator, that indicator changes color to indicate a significant change in pH has occurred. There are a variety of indicators that are used for titrations. And because we now are aware that, neutralization reactions don't always happen at a pH of 7, you'll notice all these different indicators that we potentially use if you have a weak acid, weak base combo. Actually, at pH of 7, there's only like 3 indicators that we can use. The best is bromethymol blue because it turns color right at a pH of 7, but the color is hard to determine because we're going from yellow to blue, and the in-between phase is green, and it's really hard sometimes to see that color. So be aware that there's just different indicators available depending on the type of acid and base you're reacting. So let's start to look at some acid-base titrations. So if we had a strong acid and strong base, so something like HCl and sodium hydroxide, we know that the products that we would get, right, outside ions go together, would be water and our salt, which in this case, always put your cation in front of your anion, would give us truly salt, table salt of sodium chloride. Because we're using strong acids and strong base, the pH at equivalence point should be 7. And then the indicators that you can use, again, reference the chart that we just showed you. Methyl red is an option, bromethymol blue. A lot of times we use phenolphthalein. We know that it turns color at a pH of 8, but we often just say, it's close enough that we would use phenolphthalein as well. So graphically, when you look at a titration curve, or sometimes we call them a pH curve, for a strong acid and strong base, you can tell by looking at the graph right away about what substance is in the burette and which substance is in your Erlenmeyer flask that you are titrating. So we would have our burette set up something like this. There's the valve. And then you have your Erlenmeyer flask here. This is where your pH meter would be inserted. So when I see that the pH is initially very low, I know I have an acid in there. And then what we're doing is we're adding base, slowly, drip by drip by drip inside. And then we're measuring the pH as it changes. And what we'll notice is all of a sudden in this range of volume right here, we get a drastic change in pH with very, very little addition of base added. And the equivalence point, okay, so the pH where perfect neutrality occurs is sort of this halfway point of this sigmoidal curve, okay? So this S-shaped curve is called a sigmoidal curve. And you kind of look where the steepest part of the curve is, which to me is about there. And then the halfway point is where the equivalence point exists for this particular reaction. This is showing you also some, again, indicators that we could possibly use. The best would be bromothymol blue, but this is how you can graphically determine the equivalence point of any acid-base titration. Let's look at another combination where we have a weak base and a strong acid reacting. So if we take ammonia and HCl, we notice that there is no hydroxide ion on that ammonia molecule. So what tends to happen here when we have a nitrogen base, okay, with no hydroxide, is we just do a synthesis reaction and we combine them together. When we do this, right, we notice that one of those ions came from a weak substance. So this conjugate acid is going to, make sure you put the ion on it, interact with water and set up an equilibrium. So this is a conjugate acid. So acids are proton donors. So he's going to give away his hydrogen to form hydronium. And then we're going to reform the ammonia molecule. Now we know that the ammonia molecule is a base, but it has to dissociate and produce some hydroxides when you already have a sample or a supply of hydroniums already. The pH equivalence point will just simply be less than 7. It's going to be acidic. And then you can go back and take a look at the chart of indicators. There's all kinds of possible indicators that you can use in order to determine the endpoint of this titration. Graphically, when we look at the pH curve, then we can see that, again, the equivalence point, which is sort of the steepest part of the sigmoidal curve, we'd look at the halfway point of that steepest part, and then you're going to just notice that you're going to have an equivalence point, that's what EP stands for, somewhere in the acidic range. Where exactly, we don't know. We can do some calculations to predict it, but graphically, we just should be able to see that we are at the acidic side. Again, when we look at a curve, whatever the starting pH is up here, we can tell right away what is in the flask. So I know that I'm starting with a base in my Erlenmeyer flask because this is what I would be measuring the pH of. And then we would have acid in the burette. This is the burette that we would be adding into the base. So the graph does tell us quite a bit of information. Here is a neutralization with a weak acid and a strong base. So our weak acid is acetic acid. Sometimes we write acetic acid as HC2H3O2. So just be aware, you'll see both of them. And then this is your acidic hydrogen forming water with your hydroxide. And then you'll end up with sodium acetate. So we'll just write it out this way. And then with that sodium acetate, the sodium came from a strong base, so we're not interested in it. And that acetate ion is now the conjugate base of a weak acid. So that conjugate base is going to interact with water, and bases are proton acceptors. We're going to reform the acid molecule, but again, it doesn't mean anything to us because that acid molecule would have to dissociate, release a hydrogen ion when we already have a supply of hydroxide ion left over. So the pH at equivalence point is going to be greater than 7. So possible indicators, phenolphthalein is a good one here. This is the most common one that we would tend to use, but you can take a look at the chart and see what other possible indicators we could use. Graphically, when we carry out a titration and we're recording these volumes, we usually record the volumes every, mil or two. It actually takes a while to make these curves. Then again, we're looking at this S-shaped curve, and we look for the inflection point, okay? And the steepest part of this inflection point right here, the halfway, is where we would find the equivalence point. And again, I can tell that I have acid in my flask, I have base in my burette, because initially my pH is in the acidic range. Now, when we have a titration curve for a weak acid and a weak base, because both of these are weak and both of them have conjugate acids and conjugate bases that are going to influence the pH, we know that we have to do some math and we have to determine the Ka and Kb values of the conjugates. When we actually graph a pH curve for a weak acid and a weak base, we notice that the inflection point is not very pronounced, okay, like it is with those other three combinations. It's actually a pretty sad little inflection point. And so it's best to do calculations here. It is usually very difficult to determine the equivalence point graphically for these two. Usually we rely on calculations.